Lecture number 2, Logic Gates Transformation under Boolean Algebra. Individual gates can be connected together to form a different digital function. So we have these three basic gates, the AND, the OR, and the inverter or NOT. If we have to combine an AND with a NOT or with an inverter, it is called the NAND. An OR with an inverter or the NOT, it is called the NOR. These two gates, the NAND and the NOR, are called the universal gates because they can perform any function of other gates. Then we have this expression using an AND for a variable a and b as our input. So our expression is equals to a and b or just ab. Then we can redraw this expression using an OR, a NOR, and a NAND with inverter. So for the first circuits from this expression, and we have to use an OR with inverter. So this is the equivalent circuit of an OR with inverter for your expression AND. So to prove that this type of circuit has a function the same as an expression of AND, so we have to get the equation from this circuit. So that is equivalent to your A bar with a plus sign, B bar with a long bar because we have an inverter at the output of your OR. If we have to apply the De Morgan's theorem by just break this bar into two, changing the sign from OR to AND. So we have now double negative, applying the law about double negative, then we have an expression of AB. So this is a circuit using an OR with an expression the same as an AND. So that is AB. If we have to use a NOR with inverter for that expression AND. So this is a circuit of our NOR with an inverter. So to prove that this circuit is function as an expression of an AND with its an output equivalent to AB, so we have to get the expression of this gate, that is A bar nor B bar. Applying De Morgan, so we have A double bar, B bar, then for double negative, it is equivalent to AB. So this is a circuit using a NOR to represent an expression of an AND. Then for a NAND with inverter, just by connecting your inverter to the output of your NAND so that we can get out of this double bar using your double negative, and that is equivalent to EB. For a NAND expression with A and B as input, so your expression is equivalent to A NAND B. We can draw the circuit using an OR, a NOR, and a NAND. So for an OR with inverter, so this is our circuit. We have to get the expression of this circuit to prove that this circuit is equivalent to a NAND expression of A NAND B. So we have an expression from this circuit as A bar or B bar. If we have to apply the Boolean algebra under De Morgan's theorem by joining these two bars, it will become a NAND. Then for a NOR with inverter, so we have a NOR, and then the output of your NOR must be connected with inverter. Your two inputs, A and B, must be connected also with inverter. So if you have to get the expression of these circuits, so that is E bar, then we have a plus sign of B bar, then we have double bar. So if we have to apply the double negative, it will now become E bar or B bar. Joining these two bars using De Morgan's theorem, it is now equivalent to your NAND expression. So a NAND expression, but the circuit that we use is a NOR and inverters. Then for an AND with inverter, or just put an inverter after your output of your AND. So it will become a NAND. Then for an OR expression for A and B inputs, so we have A or B, we can draw the circuit using NOR and NAND with inverter. So using NOR with inverter, so this is our NOR. We have to connect the inverter in order for the bar in your NOR must be eliminated using double negative. So we have A with a plus sign, B with double bar using double negative. So it is now equivalent to your OR expression. So with this circuit. And if we have to use an AND with inverter, so we have an AND connected with inverter and the two inputs with inverter. So the expression from this circuit is equivalent to E bar with a dot, B bar with a long bar, or that is E bar non-B bar. Applying De Morgan's to break this bar, that is equivalent to E double bar or B double bar. Then double negative, that is equivalent to A or B. So this circuit function as an OR gate. So we have this circuit, his expression is an OR expression. Then for a NAND with inverter, so we have a NAND to the inputs of your NAND must be connected to a inverter. So we have A bar, NAND B bar, applying De Morgan's. So we have double bar, applying double negative. So therefore we have E or B. So this is a circuit for your expression OR. And for NOR expression with A and B, so we have A nor B. We can draw a circuit from that NOR expression using an OR, an AND, and an NAND. So for an OR gate, we just connect an inverter to your OR gate. So that is now equivalent to your NOR. If we have to use an AND with inverter, so we have an AND connected with your inverted input. So if we have to get the expression of this circuit, that is equivalent to A bar, B bar. Applying De Morgan's theorem to join these two bar, that now equivalent to your NOR. And for a NAND with inverter, so we have a NAND. The output of your NAND must be connected with an inverter. Inputs are also inverted. So we have A bar, B bar, then double bar. Using double negative, it is now equivalent to A bar, B bar. Join these two bar using De Morgan's, so we have now a NOR expression. So NOR expression, but we are using an NAND gate with inverters. NOR gate, if we have same input variable A, that is equals to A nor A. So applying your Boolean algebra, that is equivalent to E bar. That is also the same with your NAND gate if we have the same input A and A. So that is why E NAND A. Applying Boolean algebra, that is equivalent to A bar. So these two types of gate, why it is called universal, because it can perform the previous function, and it also can perform as an inverter function. So from our example in our lecture number 2 of lesson 1 under module 2, we have this circuit. We already get the expression of that circuit and also constructed the truth table of that circuit. So now, we are going to simplify this expression using your Boolean algebra. So first, we have to determine what are these input. The first input that we have is from gate number 6. It is connected to your gate number 8 with a bar or a bubble. So we have to make this one G6 bar. So we have to put a bar in your expression because at least we have an inverter going to your gate number 8. Gate number 7 is our third input. Same, we have a bar or an inverter going to your gate number 8. So we have to put a bar on your gate number 7. And your gate number 4, it also has a bar. It has an inverter going to gate number 8. So first, we have to simplify gate number 6. So gate number 6, using De Morgan's, so we have now double bar or this quantity in a double bar. Applying double negative, then we have now eliminated the double bar. We have EC or E bar or B bar. So it can be written as EC or E bar or B bar. So if we have to multiply E bar with 1, so we have E bar and 1, that is the same as E bar under your Boolean identities. Then under also your Boolean identities, this one can be written as C or 1 because C or 1, that is also the same as 1. Then we have to distribute this inside into your parentheses. So we have EC or E bar C or A bar or B bar. So the common between these two is your C. And we have E to E bar. It is also equals to 1 in your Boolean identities. So the final simplified expression for your G6 is equivalent to E bar or B bar or C. For your gate number 7 or G7, we have double bar, applying double negative. So we have now E nor C and with E nor B nor C. Then apply De Morgan's. So we have B bar, C bar, and E bar or B bar or C bar. Then we have to distribute this B bar C bar to the quantity E bar or B bar or C bar. So for B bar to B bar, that is the same as B bar. For C bar to C bar, that is the same as C bar. So we can rewrite that one as A B bar C bar, B bar C bar, or B bar C bar. So this is the same. So we have to rewrite that is E bar B bar C bar or B bar C bar. The common between these two is B bar C bar. So we have E bar or 1, this is equals to 1. Then your simplified G7 output going to your gate number 8 is equals to B bar C bar. Gate number 4, you have just only to introduce your De Morgan to break the bar. We have E bar or B bar or C bar. So this is our original expression. This is your expression in terms of gate. Then we have to get what is your gate number 6. Gate number 6 simplified is E bar or B bar or C. Gate number 7, the simplified expression of gate number 7 is B bar, C bar. And gate number 4, we have E bar or B bar or C bar. So we have to combine. So this is your gate 6, gate 7, and gate 5. Remember gate 6, it is complemented already. Gate 7 complemented as well as gate 5. Gate 5, that is gate 4. This is gate 4. So we have to change that one as gate number 4. So this is gate 4. Now, from this simplified input expression to your y, we are going again to simplify this first by distributing your first term to the second term. So we have now your A, B bar, C bar, B bar, B bar, C bar, and we have C, B bar, C bar. So between C to C bar, that is equivalent to 0 in our identities. So 0 with B bar, it is equals to 0. So the remaining expression is equivalent to A bar, B bar, C bar. Remember B bar to B bar, that is B bar. So we have or B bar, C bar, and your third input from your gate number 4. So the common between these two is B bar, C bar. So E bar, that is here, and 1 for your other term. So this is equals to 1. So we have B bar, C bar, and your gate number 4. Distribute, we have E bar, B bar, C bar, or B bar, B bar, C bar, or B bar, C bar, C bar. B bar, B bar is the same as B bar. C bar, C bar is the same as C bar. So we have your B bar, C bar, or B bar, C bar. So this is the same as B bar, C bar. Then the common between these two is your B bar, C bar. So this is now your simplified Y. So if this is our original expression, your simplified y is just only b bar c bar. So from your original expression, this is our truth table. So from this truth table, we have also to construct a truth table for your simplified y to determine if they are the same y output. So this is our truth table, even though that your simplified y has only two variables, but the original expression of your simplified y is three variables, so therefore your input must be a three variables. Then we have to get the complement of your b as well as for your c using and to determine your y. So we have y equivalent to this one. If we have to compare your previous y from your original expression and with your y of your simplified expression, it is the same. So meaning this expression, if we have to simplify, derive just only for two variables. So if we have to draw the circuits of your simplified y, we have only an AND gate, and every input of your AND gate from B, it is connected with an inverter, and C connected with an inverter. And that's all for our logic gate transformation.